ahead and get started if we would. This is EE 523, computational neural networks. Make sure you're in the right place at the right time. What we're going to do in here today is get a little bit introduced. I'm going to go over some of the ground rules of the course and give you kind of an overview of what's going to happen, of neural networks, and some of the other contents of the course. We're going to deviate a little bit from the published abstract, and I want to make sure that you'll stay in here if indeed you're interested in such things. So we have this overhead, and you're, okay, there we are. See, it's over. There's my head. Here's the contents of the course. First of all, we're going to go through an overview of pattern recognition foundations, some of the historical and the fundamental concepts behind pattern recognition, because much of what we do in neural networks is applied to pattern recognition. In the area of neural networks, we will go over the layered perceptron and support vector machines. It turns out, very interestingly, historically, neural networks is a very, very broad field. It goes all the way from biological neural networks to things which now have evolved to the point where they no longer resemble neural networks. There are a number of journals which appear monthly and bi-monthly in the area of neural networks, such as the IEEE Transactions on Neural Networks. There's the publication called Neural Networks. There's computational neural networks. There's lots of research going on in the field. Very fascinating area. The interesting aspect, though, is that if you look at the neural networks that have been reduced to application, that about 95% of them are layered perceptrons. So that's where we're going to focus on the course, is the neural networks which have been reduced to practice, primarily the layered perceptron. There's lots of interest these days in support vector machines, which is a new type of what you could call it a neural network. However, it's just a pattern recognition principle which grew out of neural networks, which turns out to be having some very, very powerful ramifications. Where we're deviating from the course is we're also going to talk more about the general area of computational intelligence. Computational intelligence, in fact, I'd like to get the course renamed Introduction to Computational Intelligence. Computational intelligence is an umbrella over which is covered the area of neural networks, fuzzy systems, evolutionary computation, and different areas which are biologically or linguistically motivated. Evolutionary computation would include the areas such as artificial life. Maybe you've heard of genetic algorithms. That's also in the area of evolutionary computation. And evolutionary computation is becoming a very important part of computational intelligence, just gaining itself its first major journal about 2 years ago. IEEE Transactions on Evolutionary Computation, I believe, is the name of it. Fuzzy systems is a very complementary technology, although it can stand on its own with neural networks. Fuzzy systems has been reduced to practice in engineering in a number of different places. Fuzzy engineering and fuzzy systems, just like neural networks, is a very broad area. People have applied fuzzy concepts across the spectrum of just about anything that you could think of. However, if you look at what's been reduced to practice, 95% of it is what I'll call a fuzzy inference engine. And so we're concentrating in here, instead of going across the entire spectrum, of laying the foundations for fuzzy logic, laying the foundations for fuzzy systems, and then spending time specifically looking at the fuzzy inference engine. So this will be the contents of the course. And again, it's a little bit different from that which was publicized. We're going to be more interested in reducing things to practice as opposed to exploring some highfalutin theory which exists. The text for the book is the classic Read and Marks. Okay, it's available here, and when we do study neural networks, we'll be studying out of this book, and you'll love it. 5 stars on Amazon.com. And it ranks. We were really excited because, you know, on Amazon.com, they rate each of the books. I don't know if you've ever noticed that. When you go to Amazon.com, they have like the top 10 books, top 50 books, top hundreds. Well, this book broke 24,000 number 24,000 about 2 months ago, which I'm pretty excited about. It's not a bestseller, but then again, it's not meant to be a bestseller. So, anyway, it's available from Amazon. I have an Amazon link. I'm sure if you play around with the web a little bit, you can probably get cheaper prices, but you might get a copy. I noticed there's one used copy on Amazon, so if you hurry up, you might be able to get it. When we get to the area of neural networks, specifically into the area of neural networks, I'll be outlining exactly the material that we're going to be covering in neural smithing. Okay, I got carried away with the graphics here. Okay, here's your instructors. The TA is Chuni Chen. Chuni is over here. I wanted to introduce you to her. She took the course last time it was offered, did a great job, was available for to help us this quarter, and we're delighted to have her. I will be telling you about a web address and the home page for the course, and on it we'll have Chuni's email address. In fact, I do have it here. And also she'll be establishing office hours of a couple of days a week, so you'll be able to contact her. Did the camera get Chuni? She's got to be on the. You got to put her on camera. Come on. No, her. Okay. She's over here in the corner. Raise your hand, Chuni, so they know who she is. Yeah. See the camera moving in the back? You know, it's really nice because when they first started there, it sounded like robots, and you heard the it sounded very mechanical, but they've quieted that. Okay, do you have Chuni? Wave your hand again. Okay, there's Chuni. So we'll be establishing office hours for her. My office hours are as always, immediately after the class. If you have any time that you'd like to spend talking about the material or the meaning of life, I'm here to talk to you. My name is, okay, off her, back to me. Okay, good. My name is Robert Marks. I've been a professor here for a whole bunches of years, and I always forget my pointer, so let me get something to point with. I found out on watching this thing on the webcast that when you use your finger, it looks really dumb. It always looks better if you have a pointer, so I'm going to try to always use a pointer. Here is my email address. Probably the best way to get in contact with me is with the email address. Here's my telephone number. And here is the home page. Now, if you go to the home page here, which is my faculty page, you will see a little thing at the bottom right hand which says WE523. And WE523, you click on that and you will go to the home page of the course. And on the home page of the course, we'll have things posted such as the homework assignments. You will have copies available to you of the PowerPoint presentations. So you can literally download the slides that you've seen here and peruse them at your convenience. Unfortunately, this is one of these classes that I'm developing the slides as we go, so I won't always have the slides available before the class. I'll do my best, but I won't always have the slides available before the class. Okay? So those are kind of the instructors and what is going on there. Policies. These are questions which everybody asks. Number one, grading. We will have homework. That'll be 15%. There'll be a midterm, 25%. We're going to have a project later on. That will be 25% of your grade. Now, a project, one of the beautiful things about grad courses is they bring you to the state of the art in many different areas. And that's one of the things that we're going to find happening in here. You will be brought to the state of the art of neural networks, of fuzzy systems, and evolutionary computation, so that you're so smart you'll be able to lift up the transactions on neural networks and understand maybe one or two of the papers in there, which is what I do. Anybody that says they understand all the papers is lying. But anyway, there'll be a lot of papers now that you can understand in the journals. And each of you took this course for a reason. You wanted to find out about something. And we'll either cover it or we won't cover it. Hopefully we'll cover it. If we don't cover it, this is a wonderful place for you to learn yourself. As you mature as engineers, and if any of you ever become professors, you'll find out the best way to learn something is to teach a class in it. You really want to panic, you really want to learn something, offer a class on something you don't know, and you're about 3 weeks ahead of the students, and boy, you learn it well, because you don't want to make a jerk of yourself. Well, that's the same motivation that I'm going to dangle in front of you in terms of the project. We will have, for the last week or so, we will have you do a project where you research a specific area or look at a specific paper in the field from the literature and give a report on it, much like you would at a scientific meeting. And I think that you'll have fun with that. If you are really scared of getting in front of people, you can talk to me and we can do analysis. No. Maybe there's something else that you can do if you want to do a project on the side without appearing. But I think that in the field, much of your success is going to deal with the way that you present yourself and the clarity with which you can express yourself. We don't do a lot of that in engineering, so here's a good chance to do that. Then we will have a final examination, which will be 35% of your grade. By the way, this class, if you know this is weird, we meet 2 hours today and 1 hour on Thursday. I'm wondering if there's anybody that would have an objection. Let me know either by a private note or raising your hands right now if we could have it an hour and a half each day. I mean, doesn't that make a lot more sense? Now, there could be somebody that took this class because immediately after it on Thursday, you have another commitment that you have to go to. If you have to do that, we'll stick by the schedule, but I would hope that we could do that. And there's a number of reasons for doing that. Number one, I think it divides things out more evenly. Number two, in terms of the web broadcasts, you know that this course will be available in video streaming on the web. And that's kind of nice. You can go to the web and you can actually download a zip file, and the zip file will actually have the audio and the video of the lectures on them. Another thing is that this is always intimidating, but this course is going to be broadcast via tape delay on UWTV, which is the channel 27 on cable, 3 o'clock in the afternoon. So if you oversleep sometime and you have cable, you can always get up and turn to channel 27 and watch the lecture of the day. And anyway, they have it scheduled for 2 times a week for an hour and a half. So if we do 2 hours and 1 hour, it really doesn't fit within that schedule. So unless you hear from me otherwise, we'll have it kind of an hour and a half every day. If you have an objection to that, let me know either in person or anonymously. I don't even have to know who you are, and we will digress to the other day. I'd like to have 100% compliance on that, if we could. Okay, so that's policies. Let's see, the grading. Policy on academic misconduct, which is the fancy politically correct word for cheating. We go by the book on any academic misconduct. And I always know when I announce this that 98% of the people in the class are just delighted to hear this, because I know most of you don't subject yourself to academic misconduct, and when you do see it in others, you think that isn't fair, and you're exactly right. So we will enforce that for you, and I hope you're happy. I hope that you're happy to hear about that. Policy on late homework. Please no late homework. If you do get late homework, it's up to Ms. Chen whether she will accept it or not, and my advice to her will be not to accept it. Okay. If you are submitting, if you're on the EDGE program and you're submitting your homework through the EDGE office, please direct it to the attention of Ms. Chen so it goes directly into her box instead of mine, because I will take it from my box and carry it over and put it in her box, and it cuts out me, the middleman. The policy on missed tests, please make sure that you that you come to all the tests. And there are good reasons for missing tests. They're referred to, I think, legally as acts of God. You know, if a tree falls on your house or you get struck with Ebola or something. Those are good reasons to miss a test. Or you have a death in the family, for example. So that is the acceptable reasons to miss tests. The challenge with missing tests is that when a test is missed and there's a makeup, it takes me as much effort to do the makeup as it did the original test for the whole class. So therefore, it is an efficient use of time, I think you see. So we will all, if we do have missed tests, no matter what, they're usually oral, because I find that that's the best way to do that. And in fact, if I have the time, I give you all oral tests, because that's a great way to find out what people learn. It really is. cuts out the middleman of the paper and pencil there. So that's the policies on the course. The homework, I will almost always give you a week's notice on the homework. And I will give you a week's notice on all examinations so that you'll know an examination is coming up. It won't be next time we come we're going to have an exam. I'll give you at least a week's notice. It is, however, your responsibility to make sure that you keep up with the live classes. I have had on cases people come to me and say, oh, we have a test tomorrow, and I just watched the lecture that you had 3 weeks ago on the web today, and we're having a test tomorrow. I'm not ready. Well, that's not my problem. That's your problem. You need to keep up on the announcements in the class. So, in other words, my advice to you on that is to keep current. So when I say I'm going to give you a week's notice, that means live notice, okay? And the web notifications don't count. You understand what I'm mean? I like that. It's okay, by the way, if you respond to me. I prefer that because I get a feedback where you're coming from. Okay, so that's the policies. Any questions on the policies for the class? Wow, I was really clear. Okay, good. Okay, that's it for that. I thought what I'd do is start out with something different this time. And I've never done this before, but I thought it would be very interesting because it'll give you kind of a running start towards one of the topics that we're going to cover. One of the things that you do in a field is you go to different conferences and stuff, and you offer tutorials. Now, these are 1 or 2 hour presentations in which a very course overview is given of a subject so that practitioners in other fields can have a feeling for exactly what the subject is. What I'm going to give to you now is basically the tutorial which was given for some IEEE, for an IEEE interest. And in fact, you can purchase this on video from IEEE for lots of money. So I'm going to give you basically the same tutorial, and it's at a very course overview. And once we get done, of course, we will go back and we will go over this material more in detail, but I thought this might be a very good way to introduce the concept, because many times we get so wrapped up in the details that we don't see what the total overview is. So we're going to do this for neural networks. Second thing I'm going to do after this is give you a presentation of a dinner speech that I do and have done on reduction of neural networks to practice. We will talk specifically about where neural networks are being used on a day-to-day basis, not in academia, not in research labs, but being used on day-to-day basis in the area of business, industry, military, the area of finance is a very, very big area, and different areas of engineering. Bioengineering, some fascinating applications there. The area of power engineering, and these are places where neural networks have been shown to be effective tools for applications. And in fact, most of this course is going to be centered around the concept of tools you're going to add to your tool chest. I don't know if you've ever noticed, but every area of engineering is either a problem looking for a solution or a solution looking for a problem. You look at all of the IEEE societies. Power engineering, what's that? That's problems looking for solutions, right? How about signal processing? Well, that's a solution looking for problems, right? And if you go down the different areas in engineering, you find out that that indeed is the case. And so neural networks are, again, tools, so they are solutions looking for problems. And sometimes if you find the proper connection, you can do great things. And we will find out in here that the application of neural networks is just remarkable. It's been applied very successfully across the field to many, many different areas. So with that, let me give you an overview of artificial neural networks. Now, I forget what this... let me say a little bit about neural networks first of all. Neural networks were originally designed as something that, from the study of the way that the neurons in the brain works, and taking this architecture and reducing it to an engineering application. It turns out that the neural networks we have today maybe shouldn't be called neural networks because they are so far from what a real neural network is that maybe they don't even deserve the worthiness to be called neural networks. Nevertheless, they are. They can do some remarkable things, but they are remain very, very short of what any biological neural network can do. I should say advanced biological neural network. Maybe you could get an artificial neural network to do a slug or something, I'm not sure. But in terms of any human or higher perception, we're very, very far away from doing that sort of thing. One of the biggest applications of neural networks is the ability to learn things, and typically learn things from a database. How many have seen The Invasion of the Body Snatchers? Great 1950s movie. I know you have been. Nobody's seen The Invasion of the Body Snatchers? Have you seen it? What's it about? It's about these pods, and these people fall asleep, and the pod kills the person and takes on the form of the person without the soul of the person. Okay, it's really a classic movie. In fact, in Entertainment This Week, they have a book called The 100 Best Movies of All Time. Invasion of the Body Snatchers is in there, so make sure you rent it to understand neural networks. You might be able to deduct it from your taxes because I recommended it, huh? But anyway, the interesting thing about Invasion of the Body Snatchers is that these pods took on the form of the thing that they were next to. Neural networks kind of do that same thing, but typically with a database. There's typically a database of input-output relationships, and this database is generated from somewhere that it's difficult to get a model for. We're always used to putting models into things, right? If we have a stimulus and a response, we like to fill in the black box with a linear time invariant system or something like that. Sometimes we just don't have the ability to do that. So what do? Well, many times we can take, just like Invasion of the Body Snatchers, put the neural network, which is the pod, next to the data, and pretty soon the neural network takes on the same sort of relationship and performs the same sort of mapping as the original database does. So this brings us to what I'm going to call supervised learning. There's two types of learning. There's supervised learning and there's unsupervised learning. Supervised learning is when you give a stimulus, there's a response. And we are given an input or a stimulus, and there's a corresponding output, which is a response. Usually these are represented in some sort of database, or they are generated from a real-time process where data can be obtained. The problem is to train a machine to simulate the input-output relationship. We might, for example, like to train something in terms of say to learn the difference between trees and shrubberies. Now, there's two ways to do it. We refer to the material in this course as computational intelligence. It is complementary to artificial intelligence. They're not the same thing. Artificial intelligence, for looking at the difference between a shrub and a bush, would attempt to impose heuristics upon the trees and the shrubs and distinguish between the two by heuristics. For example, trees are big, shrubs are little. That's all I can think of. Is there any other differences between trees and shrubs? Trees have big leaves. Okay, shrubs have little leaves. And so by taking these heuristics and listing these characteristics, the artificial intelligence, this is a very rough generalization, by the way, would attempt through these heuristics to identify the difference between the trees and the shrub. Computational intelligence in general, neural networks specifically, would not do that. They would do the following. You have a black box, this pod that morphs itself. And you would say, okay, here's a shrub, and you would tell it, this is a shrub. You give it a bush, you say, this is a bush. No, shrubs and trees. You give it a tree, say, this is a tree. And so the pod goes, oh, okay, I think I see. And you give it a tree, say, this is a tree. Give it another tree. This is a tree. It's a shrub. And pretty soon, the pod morphs itself into such a way that when you give it a tree or a shrub which it has never seen before, by this experience which it has learned, almost void of heuristics, is able then to distinguish between a tree and a shrub. Get the idea? Without any of these heuristics. Now, there is a blurring. Many times we like to use characteristics or heuristics in order to train neural networks, but that is a rough distinguishment. That is a rough distinguishment? Is that a word? Distinction, thank you. It's a rough distinction between the two. Okay, let's talk about the object then in supervised learning, neural networks or otherwise, is to train a machine to simulate the input-output relationship that is representative of your data. There are different types, and when we're talking here, we're not talking just about the neural network. There are a number of different sorts of methods which one can apply to characterize this relationship. One is the area of classification. Now, with classification, you have discrete outputs. The shrub and the tree is an example of discrete outputs. A shrub is 1, a tree is 0. So therefore, it is indeed has discrete outputs. There's also the regression problem where we have a continuous output. Say, for example, you were to train a, well, I'll call them a regression machine to forecast the weather tomorrow, to forecast the temperature. Your output of your neural network would not be a 0, 1, but it would be a temperature, such as 45 degrees or some such thing. So it would be a continuous, an analog value. So we have discrete and continuous sorts of machines. Now, suppose that we wanted to make a machine to do this sort of thing. By the way, this again is the tutorial that we had. Here's the idea of training a classifier. I don't have a big ego, but I do use my picture a lot. We would like to do a classification. Instead of a shrub and a bush, we would like to classify between a marks, that's me, and a non-marks. So here's our little classifier. This is our little pod in Invasion of the Body Snatchers. It's going to evolve so that it recognizes the difference between a marks and a not a marks. Here's the way we would train a classifier. We would give it a marks and we'd say, hey, that's a marks. We would give it another thing, say, hey, that's not a marks. No, that's not a marks. No, that's not a marks. Hey, that's a marks. Doesn't have a beard, but it's a marks. No, that's not a marks. And you keep on presenting these different pictures to the classifier to such a degree that pretty soon, after a while, it can recognize a marks. Not only can it recognize a marks, but it can recognize a marks that it has never seen before. This indeed is the difference between memorization and learning. If you memorize, when you teach these things, you can only recognize things you've seen before. Well, you can do this with the database, right? You just do a table lookup sort of thing. But what you want to do is you want to be able to recognize things outside of the class that you use to train the neural network. So that's the important aspect here, is that it's able to recognize a marks, but the test image, it's a test image, does not appear in the training set. And again, learning is not the same thing as memorization. We want this classifier to learn the difference between a marks and not marks, as opposed to memorize. And the way we distinguish this is the way that it responds to data outside of the training set. Now, here's what we have. We're going to have what we call a feature space. And in a feature space, we have the ability to distinguish different sorts of representations. Each one of these points is a point in feature space. So let me explain what I mean by feature space. First of all, this is the way you spell Chuni's name. Okay. PA, wave chain. Put the camera on it. No, do it. Okay. I tried to get you airtime. I'm sorry. Okay. For example, what do I mean by a feature space, and how does feature space allow us to characterize different things? Well, let me give you an example, and I'm going to take men, nothing sexist meant here, but this is just the way it is, and we're going to do some height and weight. First thing we're going to do is we're going to have a number of basketball players come in from the NBA. Now, these basketball players come in, and where are they going to be in this height and weight? They're going to be pretty tall guys, right, from the NBA. So we would expect that when we have the height and the weight for these basketball players, that this height and the weight would be up here. So these would be the basketball players. I don't know. I guess as the height goes up, the weight goes up too. Okay, so these are the basketball players. And then we get some sumo wrestlers. Okay, some big guys that are sumo wrestlers. Where would they be? They'd probably be over here, wouldn't they? Right? In other words, their weight is really large, but they're not as tall as the basketball players. So we have these sumo wrestlers. Okay, so these are the basketball. These are the sumo wrestlers. And then the next thing we come in is jockeys, you know, the guys that ride the horses. Okay, short and light, right? Because they need to be short and light in order to ride the horses. So we have short and light. So down here is the jockeys. Wouldn't you agree? So this might be our training set. And what we would like to do is we would like to make a classification in that set between basketball players, sumo wrestlers, and jockeys. In order to train the set, what we'd like to do is essentially surround this data with a region. And in fact, this is normally what happens. Now, we could do this region with just looking at the data and using artificial intelligence and saying, you know, I want to kind of draw a line here, I'm going to try to draw a line here. Another way to do it is to actually let the data itself determine this. And the reason that we would like to do this is that many times our features are not in visualizable, are not in a form which you can visualize. Okay. For example, if we had 10 or 12 dimensions, you couldn't draw lines here, and it'd be really rough to do. We're doing this in 2 dimensions in order to characterize it. So we would like to do this, and we would like to be able to some way divide this up into the different regions. In fact, a layer perceptron and the classifiers that we talk about essentially do this, and they do it in such a way that the data actually characterizes this line and this partition of lines. Now, once you get done, you have learned the difference between jockeys, basketball players, and sumo wrestlers, because now you don't even need these anymore. You don't even need these data points anymore. Because now you have rules which are associated with these boundary points, and if a guy comes in and he says, okay, it's in this region, this might not even be a guy that you saw before, you say, that's a sumo wrestler, because it's on this side of the partition. Very easy sort of concept. Now you notice there's a possibility of making errors, isn't there? Right? You might get a really chubby jockey over here, or a really fat basketball player over here, right? So it isn't 100%, but you need to do it in such a manner as to best characterize your representation. Okay, with that in mind, let's go back to here what we talk about in terms of feature space. We have a feature space, and I gave you the example in the feature space of the jockeys and the basketball players and the sumo wrestlers. And again, the idea is to put some sort of boundary around the feature space in terms to characterize one class from the other. In this case, we have a binary classifier, so we have an output of 1 inside here and 0 outside here. Typically, it is assumed that there is a truth, an underlying truth which you're trying to find in terms of the neural network or the classifier, the regression machine, classification machine. And that truth is a boundary. And that boundary is something which you're trying to find. And the only evidence of that boundary that you have is the data itself. What you will do is you will supply it to the classifier, and the classifier will give you a boundary which is represented by this edge of the broken line here. And the edge, which is referred to as the representation, will generally not coincide with the truth, which we call the concept. But we can get it closer and closer and closer. How do you think we get it closer and closer and closer? We look at more and more and more data. And eventually, if we knew everything about everything, that representation would lie almost on top of the concept of the truth, right? So this is what we're attempting to do. Now, the interesting thing is, let's see, where'd I go? Okay, I didn't do that. Now, once we do that, and once we're finished training, the only thing that we have available to us is this dashed line. Throw away all the data. Once you're done training, that dashed line totally defines your classifier. And then, if this was, for example, a marks versus a non-marks, and you gave me a new representation, and it was within this dashed line, you would say, that's a marks if it lied outside. That would not be a marks. You're not going to be 100% accurate, but it will work pretty well, especially if there's no noise, and indeed the representation is close to the concept. You'll notice here, by the way, that I have these very complicated pictures, and I've reduced it to a two-dimensional plot of two features, right? When I originally presented this Marx versus A, there was kind of the assumption that we put all the pixels in there, right? Now, that's usually not a good way to do it. Rather, it is a good idea to extract, and this is where the AI and the computational intelligence overlap a little bit, is to separate some of the gross features of the individual so that you can train the classifier. I know in face recognition they do things such as the distance between the eyes, the distance between the midpoint of the eyes and the tip of the nose. Some of those different features are used to actually train a neural network, so we're not confronted with this enormous data dimensionality corresponding to every pixel. Now, just like classification, there is supervised regression. A supervised regression machine does exactly the same thing, except that the concept, the underlying truth, is not a 1 and a 0 corresponding to yes or no, but it is rather a smooth surface. And what we would like to do is to have the regression machine also generate a smooth surface so that those two smooth surfaces of the reality versus the trained machine are in some way close to each other. An example that we used in load forecasting, our lab was the first to apply neural network to power load forecasting, is to train something from historical data. This is very important in the power industry because the power industry would like to forecast the load which is delivered tomorrow so it knows what resources to put online. It used to be that every institution, Puget Power was the one that we worked with, had a guy, Puget Powers was named Lloyd, and Lloyd would go outside and he would look at the weather report, stick his finger up in the air, and do some calculations and say the power tomorrow is going to be this. And that's the way it was done. Many times they use what's referred to as linear regression. However, the world is not linear. It's linear to an approximation, but not totally linear. And he actually did a pretty good job. Load forecasting is in fact, very interesting and successful neural network application. And the training is performed from historical data. Because we have data which goes back in history, which tells, for example, what the temperature today is, the power today is, what the forecasted temperature is tomorrow, what the used power was today. And then we also know what the used power was tomorrow. In the past we do, right? On December 4th, we know the power that was used on December 5th. So that becomes the output or the response of the neural network. So the input to the neural network, and I shouldn't use neural network now because I'm trying to speak generally about regression machines. The input to the neural network would be things such as today's temperature, today's power consumption, maybe the humidity and some other aspects. Then the output is the power that is used tomorrow. Get that? And we have this big database, historically, that we can use to train a regression machine exactly the same way that we trained the classifier machine. And indeed, this works. We'll talk about, when we talk about applications of neural networks, we'll talk about literally hundreds of utilities in the U.S. and abroad that currently use neural networks to forecast their load. But this is a regression problem in that the load is not a 1 or 0. It's a continuous thing in megawatts or gigawatts or terawatts or whatever. So it's a continuous output. So therefore, this is indeed a regression machine. Now let's talk about properties of good classifiers and regression machines, just intuitively. If indeed we have this invasion of the body snatchers pod, which can take on and morph the system from which data was generated, what would we like it to do? Number one, we would like it to have good accuracy outside of the training set. This is that learning versus memorization sort of problem. We would like it to be able to learn and not memorize. That means that when you present it something it hasn't seen before, that it will respond in an accurate sort of way. Number two is to have an explanation facility. We will talk about a case maybe next time we meet, about how a lawsuit was thrown out of court because neural networks don't have an explanation facility. An explanation facility explains why this input-output relationship exists. You can train a regression machine, and this regression machine will sit there, and sometimes, if you don't care, it'll just be a black box. You don't know why it distinguished between shrubs and bushes, unless you go in there and look around, and there are people that do that. But that is referred to as the explanation facility of the regression machine. In other words, why this mapping occurs. So it is from the actual training where one can generate rules after the training which explain the reason for the mapping between the input and the output, the whys. The regression machine typically gives you the what, but not the whys. It gives you the what maps to what maps to what, man, I'm in problem. What maps to what, but it doesn't tell you the why. Getting in and understanding the why is the explanation facility. One of the beautiful things about the marriage of neural networks and fuzzy systems is that marrying the neural network and the fuzzy system generates a neural network / fuzzy system which has an immediate explanation facility which you can extract the rules from. Very interesting. Okay, what are some other properties of good classifiers and regression machines? We'd like it to train fast, right? We would like it to train very, very fast. It turns out that certain regression machines, including the neural network, don't train fast. They can take a long time to train. And the other thing is fast testing. Once you get it trained, you want a decision very, very quickly. And it turns out that neural networks do this very, very nicely. So neural networks are good on this, kind of okay on this, and they're excellent on this. I would say that 90% of the time when you use a credit card and they check your credit, it is run through a neural network in real time. And what are they doing? They're testing the data off your card. They look at the zip code. They look at the zip code where you're at. They look at what you bought. They look at where you bought it. They look at your credit history. They look at patterns of past abuse. All of these have been trained into a neural network. And you put your credit card in. All of this material goes into a neural network, most of them done by Heck Nielsen Corporation out of San Diego. They dominate currently in that market, and immediately it's checked. This corresponds to the fast testing. Now, it took them a long time to set up that system, but once it's set up, you can get the results really quickly. Because you, as a credit card customer, you don't have to stand there for an hour and wait for this thing to get chunked, right? It gives you a very, very fast result very, very quickly. I don't know how else you would get a fast result except quickly. Okay, here are some classifiers and regression machines. We're going to be concentrating on neural networks. You should know about the competition and other things that do exist because they are very, very nice and they work very, very well. And I'll actually comment on the relative performance of these. One is classification and autoregression trees, referred to as CART. This is where a data is actually used to build up a logic tree, and then the data in the classical CART is trimmed back to actually give you a classifier. It can be used for regression also. We did a fascinating study of this versus nearest neighbor lookup. Now, nearest neighbor lookup is where you have a big database, and you look at this big database, and you look at what you have, and you say, oh, is that a bush or a shrub? And so you go down your database, and you compare it to each of the things in the database, and you find the best match for the input. And then you say, the best match is down here. These two kind of look like each other. They're not exactly the same. They're pretty close. This one was a bush, so this one must be a bush too, right? So that's the nearest neighbor lookup. One of the old objections to nearest neighbor lookup is that the time to test grew as the database. As the database increases, the time to look at it also increases. You can do better by hashing the table, and I think things are speeding up where that objection is becoming less and less and less and less objectionable. There's another thing too which happens, which we'll talk about, which is a quantization which comes from the something called a Veroni partitioning, which gives kind of a distortion to your final regression or table lookup. And another way, these are just three lists, three examples of some classifiers and regression machines. A third one is neural networks. Now, neural networks we will refer to in here primarily as the layered perceptron, or MLPs, multi-layered perceptrons, because these are the ones that, again, have been shown to be most effective in reduction to application. Neural networks do a lot of very interesting and fascinating things. However, many of these things are not competitive with more conventional technology, therefore have not shown favor in the field. And so we'll talk primarily about those that have found favor. There are variations, a family of layered perceptrons, and I would count these within the layered perceptrons. They're recurrent perceptrons. Turns out the layered perceptron is a totally feed-forward animal. We also have recurrent perceptrons. Recurrent perceptrons have feedback in them. And if you've had DSP, you're familiar with FIR and IIR filters. It's kind of like the layered perceptron is an FIR and the recurrent perceptron is an IIR because it has feedback. They are very highly nonlinear animals, however. Cascade correlation neural networks, radial basis function neural networks, and there are numerous generalizations upon the layered perceptron neural networks used very effectively for classifiers and regression machines. Here's a model of an artificial neuron. And again, it's an engineering model because this is such a simplification of the underlying biology. It's remarkable. But here is the idea. We have what we refer to as a neuron, and here's our neuron. All of this little summation and this sigma sum. And what we generate from the output of this neuron is a state. Every neuron has a state or a number which is associated with it. And in here we have a number of different states, and these might be states from other neurons. This is a state from neuron 1, neuron 2, neuron 3, etc. Or it could be a stimulus. It could actually be provided a direct input into the neuron. But these are numbers also. Again, these numbers can be the states of other neurons, or they could be direct stimuli, features. Each of these is weighted, which is a fancy word to say multiplied, by a corresponding weight, and these products are summed. So the summation which comes out of this summation is simply equal to the summation over n of omega n s sub n. Now these are run through a squashing function which we will call sigma. It turns out this sum can take on a huge dynamic range. The purpose of the squashing function is typically to take the dynamic range of this summation and to squash it into a smaller interval. And so the squashing function looks typically something like this. Here could be the summation. And if you have a really, really big number, that has a value close to 1. If you have a really small number, that has a value close to 0. And intermediately here, although the graphics aren't really good, you actually have a linear sort of relationship. But you can see why they call it a squashing function, because it takes a very big dynamic range and it squashes it into a very, very small dynamic range. So this is the process of the squashing function. This is the neuron. And this is actually the neuron which is used in a large number of neural networks. And the study of the neural networks is actually the study of these hooked up and trained in different ways. We'll find out that training corresponds to determining these weights in order that our stimulus and our response morph into or do that invasion of the body snatchers sort of relationship to the original data set. Here's a layered perceptron. A layered perceptron actually has what's referred to as hidden layers. We have an input. We have, this is not a interconnect. It's an interconnect, which are also the weights. And we have this hidden layer, and typically the input is the stimulus. So if we were training for those different men, this would be the height of the man and the weight of the man. And then the output would be 1, 2, or 3 corresponding to a sumo wrestler, a basketball player, or a jockey. And this hidden layer here doesn't correspond to an actual stimulus. It just corresponds to an intermediate computation, and indeed is what the black box in the neural network is all about. In fact, they're referred to as hidden layers because they are not directly associated with an output response, nor are they directly associated with an input stimulus. Rather, they are associated with something which is happening in the middle. And part of the neural smithing idea, we'll find out that training a neural network, the name of this classic book is Neural Smithing. The reason that we call it neural smithing is that there's still an art to training a neural network. For example, when you choose a neural network, we have a hidden layer. Well, how many neurons do you put in the hidden layer? How many layers do you put? Okay, how do you know whether to use feedback or not? What sort of features should you use? Is it better to use more features? Is it better to use less features? Is there a way where you can actually take the features and combine them in some way to give you a better response? So there's a number of interactive sort of dictates in training a neural network. But this is the basic component of the layered perceptron. Now we talked about the recurrent neural network. The recurrent neural network would have feedback. This is a feed-forward neural network in the sense that the input directly flows to the output. We could also have a recurrent neural network where there was feedback associated with, for example, this state feeding back and feeding an input node. And there are, again, a number of variations on this. So here's the problem. Giving the training data, we have an input vector set. This is I sub n. So for the example that we use for the jockeys, basketball players, and sumo wrestlers, this would be the weight and the height. So n would be equal to 2, corresponding to 2 features, the weight and the height. And what we would like to do is we would like to have that weight and the height correspond to what we refer to as the target vector. The target vector is what we want. So in the training data, this might be a small height and a big weight, so the target vector would correspond to a sumo wrestler. And we might assign a 0 to a sumo wrestler, a 1, well, probably a 0 to a jockey, 1 to a sumo wrestler, and 2 to a basketball player in terms of the output. We could do that. And so that's the target. That's what we would like to do. Now the problem in training the neural network is to actually find the weights of the interconnects using training data to minimize the error in some way. Let me explain to you what I mean by that. Here we have the input. Let's just take the weight and the height. Here's a rough explanation. Here's the hidden layer, and here's the output layer. 0, a basketball player. Let's just do basketball players and sumo wrestlers. Okay. We put a weight and a height in here. We run it through our neural network, and suppose that we know this weight and this height correspond to a sumo wrestler. A sumo wrestler is going to be a 1, and a basketball player is going to be a 0 in this example. So we put in a sumo wrestler, and we get out a 0.2. Well, this is what we get, right? But that's not what we want. What do we want? If it's a sumo wrestler, what do we want? We want a 1, don't we? So there's actually an error here. And what we do is we take the difference between the two and we adjust these weights in such a fashion that the next time we see that sumo wrestler, that output is a little bit closer to the 1. And then we can do that with every single one of the training data until eventually, after we've adjusted these weights for a while, we're going to get the case where we do the same sumo wrestler and maybe now we get a 0.9 and the output is a 1.0. So that's close enough in order for us saying that our neural network is trained. So we go through the entire training data set. The problem is that once we go through the set, when we get to the end, we might have forgot what we learned in the beginning, right? So we need to repeat it. In fact, you typically have to go through the data set a number of times in order to adjust these weights so that finally the input-output relationships are trained. I'm going to go through a little math. You're not going to be responsible for the math here. We will later in the course go over the math a little bit more in detail because it's very beautiful and eloquent. If there was a Nobel Prize for engineering, I think this would win it. So here's the situation. The error. What is the error? We look at the input values. We look at the output values. Now the output values is what you get. The target values is what you want. The difference between what you want and what you get is the error. And so this is what we refer to as the error, and we sum them up over all of the training data. Say we had 1,000 different examples of sumo wrestlers and basketball players. We would put all of those in, and we would take the difference between the outputs, the what we got and what we want, and we would call that the error. And what we would like to do is we would like to change the weights in such a fashion as to reduce that error. Let's look what the error is a function of. The error is only a function of the fixed training data and the test data. It's also a function of the neural network weights. The problem is to find the weights that minimize the error, which is referred to as standard optimization. But it's nonlinear optimization. Here's the idea. We have the inputs, we have the outputs. And then we have all of the weights. Weight 1, 1, weight 1, 2, weight 1, 3. And then out here we have our data set. We have our I sub n's and our outputs, our corresponding outputs. So sumo wrestler, basketball player. So these are the relationships that we have. Now what's interesting about this input-output relationship is that this data fixes the error. If we have a specific set of weights, and just to visualize, suppose we only have 2 weights. I know we have hundreds of them, but we only have 2 weights. We have 2 weights, and we choose this weight and this weight, corresponding to this interconnect and this interconnect. I know we have a bunch more, but just for visualization purposes, suppose that we had 2. We choose these 2 weights, and then for this given data set, there's an error which corresponds to using those weights. See, we don't know what weights to use. But if we choose 2 weights, we can figure out what the error is. Again, we have this data set, we have the weights, we have the input-output relationship of the neural network. So there's an error associated if we use a weight of 1 here and a weight of 1 here. If we change this weight to 2 and keep this one a 1, well, then we're going to have another error here, which is 2. So no matter what weight we choose, every coordinate in this space corresponds and is assigned a different error, isn't it? In fact, this error, if we were able to explore the entire space, this error would look like a mountain range in general, wouldn't it? It would go up and down. And so we can actually talk about this error space as a function of all of these weights if we did a contour plot of this sort. And say this is a bowl. If we're training this neural network, what might be the error that we're interested in finding? The minimum. We would like the weights which for this data minimize the error. So what we'd like to do is we'd like to find this point here. If we found this point, we would be able to get the optimal weight for 1. We would be able to get the optimal weight for 2. And that's what we'd like to use maybe in our neural network. Does that make sense? Does that make sense? Does that make sense? Now, the question is, how do you do it? Well, one of the things you could do in optimization is you could, by the way, we're going for an hour and a half. What I'm going to do is I'm going to go with no breaks, and let's see, how does that work? A class is 50 minutes, right? So what's 1.5 times 50? 75 minutes, right? So if we go without a break, I dismiss you at a quarter till, right? So that's the way I'd like to do it. We could take a 5-minute break in between, but that's up to you. Would you rather just go the marathon? Do it. Okay, so what are we talking about? Every way that you have a weight here, every different choice of weights, you get these. You get a different error associated with it. This is called the error landscape, if you will, because it's kind of like bumpy hills and such. And we would like to find the case where the error is minimized. How do we do this? Well, one way to do it is by exhaustive search. We could actually set up a computer program, and we could do a little oscillation through the weights here, and we could check every different set of combinations of the weights and see what the error is for those weights for this given input and output. These are given. We could do that. The problem is if you have something like 10 features, say 10 inputs, and you want 10 points in each dimension, you get about 10 to the 10th points that you need to do. This number gets really big, really quick in order to do an exhaustive search. So we would like to do this search a little bit more cleverly. And there's a number of ways that this search can be done. There are people that get their PhDs in the area called operations research. Their whole lives are concerned with landscapes and trying to find the minimum of these landscapes in order to perform optimization. And that's exactly what this is. It's an optimization process. And there's a number of ways that we can do this. One of the ways, which is an old way, and actually not a very good way in one way, but it's a very good way in another way. It has good features and bad features, is steepest descent. We can imagine ourselves as this is the bottom of a valley. And what we want to find is the absolute bottom of the valley. And we're just a blind guy. Okay? And we're standing on the side of the hill, and we want to find this. So what do? We're just like the neural network that we know the response to these weights. One of the things that we can do is kind of look around and see which way we go downhill, right? And once we see which way we go downhill, we'll take a step in that direction. And if we step downhill, well, we'll be closer at least. So that's the idea of steepest descent. We find out which direction is steepest, and then we take a step there. So that's the idea of steepest descent. So we take a step downhill, we take a step downhill, we take a step downhill. Now you notice that this, as well as many other search techniques, has a parameter associated with it. In this case, it's the step size. Should we take itty-bitty steps, or should we take really big steps? That's a neural smithing sort of problem. Or should we look at the history of our steps and maybe adaptively, dynamically adjust the step sizes? We can do all sorts of fun things. But the interesting aspect is that this convergence is very similar to that which you would see in control theory. Because you imagine if we have a bowl here and we take humongous steps, we go here, 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 here. What does it remind you of? It reminds me of a control system where we have this as our fixed point and we just oscillate. We finally get there, but boy, we have to wiggle around things quite a bit in order to get there. It's a very underdamped sort of system if we take too big of a steps. If we take little baby steps, yeah, we're going to get there, but it corresponds to what? An underdamped, an overdamped sort of system, right? Very similar concepts between that and control theory. But you see, steepest descent is not the only technique we can do in order to find this minimum. Training a neural network boils down to finding this minimum under some additional constraints. Like maybe this minimum won't generalize well. We've got to make sure that whatever minimum we find generalizes well. That is, will respond well to data outside of the training set. But if we're just worrying about finding the best set of weights to minimize the error corresponding to the training data, that this is what we would like to do. So we want to find the weights that minimize the error. This is standard optimization. There exists a plethora of different ways to do this, including conjugate gradient descent, random search. Random search is kind of weird. You're the same blind guy, and what you do is you put your foot out randomly all around. If it's downhill, yeah, you go there, right? If it's uphill, you put your foot back and try something else, okay? And that corresponds to random search, and it works kind of cool. It works kind of nice. And in fact, genetic algorithms and evolutionary search are generalizations of the concept of random search, we'll see. And then we mentioned also steepest descent, which turns into a beautiful algorithm called error backpropagation, which we can apply specifically to the layered perceptron. Okay, here's the idea of steepest descent. It's exactly the way that I mentioned it. It has an old history, but was actually popularized in the area of optimization by Bernie Woodrow and his graduate student Hoff, and is sometimes referred to as the Woodrow-Hoff algorithm. Bernie Woodrow is a professor emeritus at Stanford right now, so he's still around. So the question is if you are going downhill, so you have a one-dimensional gradient, or one-dimensional landscape, if you will, and you want to go downhill, how do you go downhill? Well, it turns out downhill is minus the derivative of where you're at. So if you take the derivative of where you're at and negate it, that is going downhill. So if the new value that we have is equal to the old value minus eta, which is your step size, remember you take a little step size or a big step size? So if your new value is equal to your old value minus eta times the derivative of the error with respect to the variable, then you're going to go downhill. Usually going downhill is not a positive thing. Here it is. And eta is the corresponding step size. Now there are other things which are fraught, and these are not problems with gradient descent or steepest descent or anything else, but they're general in optimization. You might have other things over here where these are contours. That's a minimum too, but this is a deeper minimum than this. This happens all the time. And maybe if you use steepest descent, you get caught here when you really want to be here. And if this is like 50 times, if this is 50 times lower than this, that's not good. You have to figure out a way to jump out of it. And this is a problem which you have to avoid. And steepest descent will get you caught in these areas, which are referred to as local minimum. because you might have local minima at different places. What you want to find is the global minimum, the best minimum that you possibly can. Now, here is the example of steepest descent. Actually, it's a math example, and I won't go through this right now because I don't want to get us embroiled in the math yet. We'll have plenty of time to develop that in a more careful manner. And I also won't get into that, nor will I get into that. Or this! Or this. Or this. Or this. I will tell you, though, I'm going to give you the gestalt of error-back propagation, which is steepest descent applied to a neural network. Steepest descent has its faults, but there's a couple of very beautiful characteristics about steepest descent. Number one, it allows us to know when to stop the training of the neural network. That's very nice. Number two, it has a beautiful aesthetic biological property, and that biological property is as follows. Error-back propagation, by the way, was initially done in 1974 by Paul Werbos. And Paul right now is a program manager for the National Science Foundation, and he is actually a program manager of one of the projects that we have right now. Well, he and it was for a Harvard PhD thesis, was the first to invent error-back propagation. Error-back propagation was one of those things waiting to be discovered. And just like in the, I don't know if you've heard of these, the Gershberg-Popoulas algorithm. Turns out a guy named Gershberg and a guy named Popoulas developed the same algorithm independently of each other and didn't know about each other, but they were exactly the same algorithm. There's the, oh man, what's the name of the singular value decomposition? Kohonen-Loew expansion? Anybody heard of the Kohonen-Loew expansion and probability? Kohonen-Loew, totally independent of each other, developed the Kohonen-Loew expansion. Just like Newton and Leibniz. Put them together, you get Newton. Newton and Leibniz both invented the calculus independently of each other. So this sort of thing seems to happen all the time. It happened in error-back propagation. It happened with Werbos. Historically, Werbos was the first to do it, but it was followed up later by Parker and popularized by a Stanford psychologist who was interested in the biological operations of neural networks, known as Dave Rumelhart, who passed away about a year ago. So Paul Werbos invented the concept of backpropagation, and I want to end the class by just telling you what the beauty of error-back propagation is. If you have a neural network, and here's a neural network with all sorts of interconnects, when you get what you want minus what you get, and you square it in order to get the error, what you have to do is you have to go back and you have to adjust all of the weights in the neural network in order to reduce this error next time you see the same training data. That's what you want to do. The beauty of backpropagation, which we'll see in detail when we get to it, is that backpropagation does the following. It sets up parameters at every node, a set of 2 parameters at every node. And the first set of parameters is determined by going forward, the second one is determined by going backwards. And once these parameters are determined, the weight change in each one of the weights is determined only by the 2 neurons which connect it. And that's beautiful from a biological point of view, because if you were doing this biologically, this is a property that you would want. You would want things to happen in a localized manner. Even though the optimization is over the whole thing, the beauty of error-back propagation is that it does this whole optimization by being able to do it just neurons at a time. And it's really nice from a biological point of view. We need to ask, though, as engineers, do we care about that? Actually, we don't. Unless you want to force your life into... It's very nice to program, like in object-oriented languages, because it's very modular in that sense. But despite the modular nature, do we really care about the fact that our optimization is to be done locally? Actually, maybe a little bit, but not really a lot. We're more interested in the actual results as opposed to how they're done. We're interested that the neural network be trained in a successful manner as opposed to the manner in which it's trained. And so this is a beautiful biological result, but it really isn't applicable to engineering things very well. One of the nice things about backpropagation, or any algorithm which defines things in terms of steps, is, I said this would be the last thing. I lied. I'm going to do one other thing. Is that every time you run through a data set, it's referred to as an epoch. So we have this big data set of basketball players and sumo wrestlers, and we go through this big epoch, we get the error and we backpropagate it, and once we get down to the end, the thing that we've done in the beginning, we've forgotten, so we got to go through it again. And then we got to go through it again. And every time you go through an epoch, what happens to your error? Well, in general, the error changes, or the error decreases, right? The error decreases. In fact, if you have enough neurons, the error will eventually go to zero. But remember, one of the things that you wanted to do was to learn, not memorize. Learn, not memorize. And eventually, if you don't watch yourself, you begin to memorize. How do you keep yourself from memorizing? Well, you save part of your training data set, and you put it aside, and you don't use it to train. It's called the test. Because you want that neural network to do what? You want it to respond to things that are outside the data set, right? In a successful manner. In order to assure that the neural network responds favorably to data outside the training set, you have to make sure you have data which is outside the training set. So you take part of your data and you just set it aside. And then what you do is you use part of the data to train your neural network. And then as you're training the neural network, you look at this data that you've set aside, which is the so-called test data, and you will find out that the test data also goes down. This is the data that it hasn't seen before. And then many times it will flatten out, and then it will start to go up. As soon as it goes up, you're starting to memorize, because it recognizes things within the data set, the things that you have set aside, it's not recognizing, right? So right here is a good place to stop the neural network in terms of training and use these weights, because this is the balance between the training and the memorization. We will get more into detail in this concept later on when we talk about backpropagation. Again, we're talking about the overall tutorial. So this is the weight update, and this is the actual details of neural networks and some other factors which we will deal with more in later. Okay, any questions at all? I'll go through a few of these things to finish up and polish up next time. Are there any questions at all? Okay, thank you. We'll see you on Thursday.